We're going to move on to the topic that we're going to discuss for about the last third of the course, which is probabilistic graphical models. So we've been focusing so far on probabilistic models, and generally the way we've approached each model is we devise some specific model given some set of random variables and their associations with one another, and we figure out how to do inference for that specific model. And sometimes there are some small things we can tweak. For example, in the case of, let's say, a naive Bayes network, we can have a variable number of features, and those features can have variable types. But in general, we have engaged in the paradigm where we devise a model and then figure out how to do inference specifically in that model. So in this section, we're going to go up a level of abstraction. We're going to think about probabilistic models in general, and we're going to look at for general cases of sets of random variables and broad categories of how they're associated with one another, how we can do inference in that case, and how we can do it efficiently and precisely. So we're going to look at a couple of different ways to do that and talk about some of the advantages and disadvantages of those methods. Before we talk about Bayesian networks, let's briefly remind ourselves about independence of probability distributions. We say that two random variables, A and B, are independent, and we write it like this: A independent B. We say that if it's the case that probability of A comma B equals probability of A times probability of B, or equivalently, the probability of B given A equals probability of just B. Okay, so that's what it means when we say that two variables are independent. We can also assert conditional independence. That is, we can say that A is independent of B given some other variable C, and that is an independence property that occurs when we're given some other random variable. So we have exactly these same properties, just given C. So we can write that out. Probability of A comma B given C equals probability of A given C times probability of B given C. Equivalently, probability of B given AC equals probability of B given just C. Okay, so notice that this is what I've written down here is exactly the same as up here, except that C just appears everywhere in the conditions. Okay, so that was your brief review of what it means for two random variables to be independent. We're going to look at roughly two categories of probabilistic graphical models. Those are Bayesian networks, which is our directed probabilistic graphical model, and in a little bit we're going to look at Markov random fields, which are our undirected probabilistic graphical models. By the way, the term probabilistic graphical model, well, probabilistic model, we know what that means. By graphical, we mean that we represent the model through a graph, that is a collection of nodes and edges. So we've discussed Bayesian networks before, but let's just briefly recall what a Bayesian network is. So in a Bayesian network, we represent each random variable as a node in the graph, and we put an edge from A to B, indicating in some sense that A directly influences B. I'll be more precise about that in just a minute. And that's our network. So this is a directed graph and a directed probabilistic graphical model because these are directed edges. That is, they're an arrow with a source and a destination, a parent and a child. One thing to note about Bayesian networks is that a Bayesian network must be a acyclic graph, a directed acyclic graph, DAG, directed acyclic graph. That is, it can't have any directed cycles. That is, we couldn't have an edge from E to A, for example, because that would form a cycle A to C to E to A. Notice that there are, in some sense, loops formed by edges in an undirected sense, in the sense that we have edges among all these four nodes. Just note that there's no way to start at one edge and follow, or start at one variable or one node and follow directed edges in some way that would get us back to the one we started with. So in that sense, it must not have, the graph must not have directed cycles. So one property of directed acyclic graphs is that they have what's called a topological ordering. That is, we can write the nodes in some order such that parents always occur before childs in that ordering. So a valid topological ordering for this graph would be A, B, C, D, E. Another valid ordering would be A, C, B, E, D, and so on. So notice, if we look at this ordering here, A, B, C, D, E, notice that A is the parent of B, so A occurs before B in the ordering. And likewise for C and D, B and D, C and E, and so on. And these are both valid topological orderings. So that's an indication that there can be multiple valid topological orderings. But there's always at least one valid ordering for every directed acyclic graph, and therefore every Bayesian network. An example of a non-topological ordering would be something like A, B, E, D, C. Notice, for example, that C occurs after E, even though C is a parent of E. That's a property that we're going to use a couple times coming up. So notice that it makes sense that a Bayesian network must be acyclic because it indicates, in some sense, causality among the variables. So it can never be the case that if A causes C, then C can somehow simultaneously also cause A. That's just sort of not possible when we think about causality. Now notice that if there's a feedback loop, let's give an example of a feedback loop. For example, in an economy, for example, maybe prices influence wages, and then wages also influence prices, according to some maybe complex economic model. So our first thought might be to draw a Bayesian network that looks something like this. The thing to realize is that that they evolve over time. So we're not going to spend a lot of time on dynamic Bayesian networks. I'll mention them briefly. But notice that if we were to model prices and wages, we would have to show that they have some evolution over time and that prices and wages at the previous step influence them at the next step. So let's say 1 year to another or 1 month to another. and therefore we would have a network like this, and this would go forward in time. But now notice that this network does not have directed cycles. So this is a valid Bayesian network. So that's just one thing to remember, that Bayesian networks must always be directed graphs. If you have something that you think is a feedback loop, it's probably a feedback loop over time rather than kind of somehow simultaneously. So I said that a Bayesian network represents a probabilistic model, that is a specific probability distribution over the variables that we've observed. To have a probability distribution, we need this network, and also one more thing. We also need to have a conditional probability table, CPT, associated with each variable of that variable given its parents. So since in this Bayesian network we have 5 variables, so we'll need 5 CPTs, and they're going to look like this. Okay, so these distributions in red are the ones we'll need to specify the distribution for this Bayesian network. We'll have probability of A given nothing, because it's just because it doesn't have any parents. Probability of B given A, C given A, because each of them has just one parent in this network. D given B and C, because it has both parents, and probably E given C. So I'll explain why in case it's not obvious, but given all of these conditional probability distributions, we get a full joint probability over our 5 variables. Okay, let's convince ourselves that this is a meaningful thing to do. So let's say that someone hands you a Bayesian network represented by this graph over 5 variables, and a conditional probability distribution associated with each random variable. So we're going to show that we can generate the full joint distribution based on just those conditional probability distributions. So here's the thing that we want on the left, the full joint distribution between our random variables. To figure out what that equals, we're going to apply the chain rule. So recall that when we apply the chain rule, we pick one variable, let's say we pick x1, we show that the probability of all the variables, by the way, I've written this joint distribution as x1 to v, that is all the variables 1 up to big V, which is the number of random variables, in this case 5. When I apply the chain rule, I get this. Probability of just x1, the variable we chose, times probability of everything else given x1. Then I can apply the chain rule again to this thing. I'm going to choose x2. I get probability of x2 given x1, because that's already in the condition, times probability of x3 to v given x1, x2. And then I can continue. So if I keep doing that, and I do this in topological order according to the Bayesian network, notice that I've pre-ordered the variables 1, 2, 3, 4, 5 into a topological ordering. I get the following, that our joint distribution equals this thing, probability of x1 times probability of x2 given x1, x3 given x2 comma x1, and so on all the way up to xv given everything else. Now, there's something else that's asserted by the Bayesian network. So I said a couple of slides ago that an arrow from x1 to x3 indicates in some sense that x1 directly influences x3. And here's what I mean formally by that. I mean that given x1, x2 is independent of everything else in the network. And that's true in general for any variable given its parents. So as another example, x4 given x2 and 3, its parents, is independent of everything else, x1 and 5. So these are called conditional independence properties, and they are asserted by our Bayesian network. So when I draw a network like this, I'm not really indicating conditional dependencies. I'll talk about that in a minute. What I'm really indicating is conditional dependencies. That is, for this network, if I've drawn it like this, it's impossible for this not to hold. x2 is, it must be the case that x2 is independent of everything else given its parent. Okay, so that's what the graph asserts. So now let's see what happens when I apply this to my chain rule. So note, let's look at this term here. I said that x3 is independent of everything else in the network given x1. So that is that x3 given x2 and x1 is identical to x3 given just x1. So I can take that out of the condition. I can do the same thing for x4. x4 depends just on x2 and x3, so I can take that out of the condition. And let's look at our last term, probably of x5. When I write it in the chain rule, it's dependent on everything else, but I can cross off everything except x3 because the network asserts that x5 is independent of everything except x3. So now note that look what I have in my chain rule. I have that if I want to know the joint distribution of any assortment of random variables, I just have to multiply together these 5 conditional probability distributions. And note that those distributions are exactly what is specified in the conditional probability distributions that I said you gave me, or that someone gave us when they gave us this graph. Probably x1, x2 given x1, x3 given x1, and so on. So this is just to convince ourselves that if someone gives us a network and gives us those conditional probability tables, they've also given us a full joint distribution over our random variables. So just one thing to note is I said that a Bayesian network indicates conditional independence properties, but it doesn't specifically indicate conditional dependence properties. So why is that? Let's say I give you this Bayesian network, and I give you some distribution for A. I don't care what that is. Let's not worry about that. And then I give you a distribution for B. Let's say I give you this distribution. So we're going to write this as a table. We're going to say, what's the probability of B for the different values of A. Let's say both of our variables are binary random variables, so A can be 0 or 1, B can be 0 or 1, and whatever, let's say I give you this distribution here, probability of B given A is 0 is, let's say, 0.9 probability B equals 0, 0.1 probability B equals 1, and the same if A equals 1. So you might notice, oh, but look, the probability of B is the same no matter what value of A I give you, which is to say that, in fact, A and B are independent. And in fact, a perfectly valid way to write this graphical model would be to throw away that edge. So now you would probably say, okay, why in the first place did you put that edge in your graph? You could have gotten rid of it and it would be equally valid. But we allow ourselves to put in edges that are unnecessary. That is, I'm still allowed to put an edge from A to B even if A and B are in fact independent. So the reason for that, we could imagine some alternative definition of a Bayesian network. We could say that we're only allowed to put an edge from A to B if they are truly dependent and not independent. I think that would make our lives difficult because let's say we wanted to make a network over A and B, but we're not sure yet if they're dependent or independent. Then we wouldn't be able to even draw any graph because any graph we might draw would end up being invalidated later if we perhaps discovered that A and B were independent. So the reason we kind of allow ourselves this flexibility, we say that, okay, you're allowed to put edges between things even if they end up being dependent. That kind of lets us off the hook to decide before we even get to write a graph down whether two variables are dependent. Okay, so really that was just a note to say that if I take away that edge, I'm asserting that A and B are independent. So that is to say that my Bayesian network can assert conditional independence properties, but Bayesian networks never assert conditional dependence properties, just because we don't want to force ourselves into having to make that call. So if you're not sure and you want to be able to write a valid Bayesian network, it's perfectly valid to kind of connect everything. I'll talk about that more in just a minute. Okay, so now let's imagine instead someone hands you a joint distribution. It turns out that given a joint distribution, you can construct a Bayes net based on that. So let's say I have this joint distribution. From the joint distribution, again, I've just applied the chain rule in exactly the same way. From that joint distribution, I can look in it and I can see what is probability of x1. This thing is just sum over everything else of the joint distribution. So that is, given just the joint distribution, I can calculate the probability of just x1. Same thing for x2 given x1. I do that. Well, this thing equals P of x2 comma x1 over P of x1. I already showed you how to calculate x1, P of x1 rather. I can calculate P of x2 comma x1 in exactly the same way. I do just the same thing here, except that when I when I give you a particular pair of variables that I want to calculate the probability for, you sum over everything else other than those two, and then ask what the values of those two are. Now, I'm not saying this is a computationally efficient way to calculate these probabilities, but in principle, if someone hands you those, this full joint distribution, you can mathematically calculate each of these conditional probability distributions. So now I can draw a Bayesian network. It's not going to be a very useful Bayesian network, but here it is. So x1 here doesn't have any parents. x2 has just x1 as a parent. x3 has x1 and x2 as a parent, and so on. This one's going to have 3 parents, and this one is going to have 4 parents. Did I miss one? No, that's good. Okay, so this is not something that happens very often, but just to convince ourselves that we can flip back and forth between these two representations, a Bayesian network is a way to represent a full joint distribution. We can also think of a full joint distribution as a way to represent a Bayesian network, because we can always construct a Bayesian network and the associated conditional probability distributions based on given just that full distribution. And by the way, if we were to look in the joint distribution and notice that any of these conditional independence properties hold, then it's possible we could delete some of these edges. And by the way, note that I can do that with any ordering of the variables. I could do this just as easily with x5, x2, x1, x4, x3, and I would get the same structure. So perhaps everything I just told you was obvious. So that was just a couple of different properties of Bayesian networks, that is, showing how we can swap back and forth between the two ways we could represent some probability distribution, that is, a full joint distribution, or a Bayesian network where we have a conditional distribution of each variable given its parents. By the way, so far in this course, we've normally used that second representation. That is, we've normally defined our probability distributions as the conditional distribution of each variable given the things it depends on, rather than just some gigantic full joint distribution. So in this section, again, we're discussing probabilistic inference kind of in general, where we're trying to go up a level of abstraction and try to come up with algorithms that are general for many different probabilistic models. So one might ask, okay, why use Bayesian networks? Why not just, the first thing we do is whatever form a person gives us a probabilistic model in, one way to do all our inference is we could just form that joint distribution and then do all of our inference relative to that. So there are a couple of reasons that we prefer using Bayesian networks or other types of graphical models that I'll talk about in a second over that joint distribution approach. Number one is that having the Bayesian network is kind of visually useful to look at. It gives us just from the network, it gives us an understanding of the properties of the model. Again, specifically the conditional independence properties. The other reason is that Bayesian networks are generally much faster to perform inference and learning on, and they have many fewer parameters. So let's see why that is. Let's look at a specific example. let's suppose we have a case where we have n binary random variables. Let's say we wanted to store that distribution as a full joint conditional probability table. How many parameters do we need to specify that? Well, I can encourage you, by the way, to pause the video and answer these yourselves. But I'm gonna go straight. So here's your chance to pause. Okay, how many parameters do we need to store the full joint CBT? Well, we need 2 to the n. That's the number of possible assignments to those n binary random variables. If we're going to be especially smart, we can realize it's actually 2 to the n minus 1 because the distribution has to sum to 1, and therefore we don't actually, we could give just the first 2 to the n minus 1, the last one is implicit, but that's not too important. Okay, so that's the answer to the first one. Okay, what about if we have a Bayesian network assuming each variable has k or fewer parents? Well, in that case, our distribution is going to be given to us. We're going to have k conditional probability tables. So it's going to be k times something. And each of those conditional probability tables is going to have 2 to the k entries. And again, we can note that the number of parameters required to specify that is actually 2 to the k minus 1 because each one has to sum to 1. So this is the number of parameters we need for that. Sorry, this should be an n because we have n different variables. Hopefully you caught that as I said it. Okay, so here's our solutions. Now let's give an example of like what happens if n equals 100. Let's say n is 100 and k is 2, so each variable has just 2 parents. If we tried to write down the full conditional probability table, that would have 2 to the n entries, which is 2 to the 100, which is roughly 10 to the 30, somewhere around there, versus if we wrote this as a Bayesian network, each table has just 2 to the 2 minus 1, that's 3, times 100 variables. So 300, which is totally manageable, no problem, versus 10 to the 30, which is probably straining even a really modern computer. In fact, that's probably way too much to store on even kind of your giant memory mapped hard drives these days. Okay, so that is when we're interested in doing inference over really large probabilistic models, even one that has as few as, let's say, 100 variables, which actually isn't that many in the scheme of things. When we have kind of big data sets these days, they could easily have thousands or even millions of variables. Even once we get to 100 variables, trying to write down a full conditional distribution is no good. Even just from a memory perspective, it's much more efficient to write down the Bayesian network. So this has a bunch of consequences. The simplest one is just a memory issue. We wouldn't be able to store that giant distribution even if we wanted to. It has consequences in terms of running time. Even if we could store the distribution, anytime we wanted to do any kind of inference over it, usually we would have to iterate over all, in this case, 10 to the 30 entries, which would be really, really slow. But perhaps most importantly, generally we want to learn our probabilistic models from data, and the number of parameters we can afford to learn depends on the number of examples we have. So unless we have a truly enormous amount of examples, we're never going to be able to learn 10 to the 30 parameters. Whereas with even a moderately sized training set, probably learning 300 parameters is not a big deal. Okay, so for all those reasons, generally when we want to do inference over kind of general purpose probabilistic models, it's only for the smallest models is it going to work to use the full joint distribution. In any other case, we're going to need to use some kind of probabilistic graphical model like a Bayesian network. So this is why we're going to be focusing on Bayesian networks and probabilistic graphical models here.